so I start with quoting, I will systematically quoting people, because many things of general type have been said by people who know really the subject matter better than I do. And so it will be worth listening what they say, and then you may agree or disagree with this, of course. Yeah. And this is the first point said by Buffon a long time ago. And the issue here, at which stage it was realized that by scientists kind of think about life, that in principle they don't understand life. So you need a perspective. Why they didn't understand it? And then just a few remarks historical. But again, when I speak about history, it's kind of imaginary history. Being truly say something about history of science, you have to spend your life on each particular issue. It's very difficult. So yes, what I'm saying is common opinion about history, which maybe unusually is not correct. Yeah? So before a certain moment in history, life was well understood, and moreover, everything else was explained in terms of life. Yeah, it's called animism, and it's still like that. Yeah, for naive mind, life, everything which moves is alive, and say cars are alive, say for a boy, and accordingly, rivers or or clouds were alive for simple people a couple of 3,000 years ago, and life is much easier was to describe. And you easily describe life, even now, because both our sensory system, in particular vision, is adapted for life. So when you develop these artificial vision systems, you can immediately see that they're very different. We recognize life very fast, and looking at this picture with this cow, you immediately can make a story about that. But if you look at this, by the way, what is this probability? Well, mathematics, of course, yeah, you have to know something. That see this geometry in these formulas, and this is mathematics, which is interplay between two ways of thinking, numerical and kind of geometric, say. And then there is physics, when starting from beginning of the 19th century, it was very much perceived as a statistical analysis of data and interpretation of the statistical data. It was articulated, at least, well, by many people, but Maxwell specifically, in a very kind of, is well understanding of that, because he was one of the first who developed statistical mechanics of atomic level. But what, by the way, in this picture, this brownish picture, what's all about and how we can describe it. So there is no words in the human language to properly describe it, right? Unlike this cow, and there is the sky, and these people, and the cow is sleeping, and these people are walking. You can say long things, say. It's nothing to do with what you call science, right? And then there is this landscape, and then landscape of Mars, and certainly what it is a sample of some random field, yeah? So apparently there is a random field behind this picture, and the laws would be finding the probability laws. And then you see this sample, and there are many other samples we can make, and this, from which you can recover this stochastic law. By the way, how we recover this, right? We have samples. How we recover statistic laws? Yeah, of course, it's a non-trivial point, and usually you do it by looking for already kind of standard laws, like Gaussian law, some other simple law, and just adjusting it. And this, how we do this, there is, of course, no recipe, yeah? And this actually will be relevant for basic features of life. There are two kinds of randomness. One, you perceive this on the picture, the sample of something, and then there is a law, random distribution behind it. Of course, this random distribution depends already on some mathematical formalism, and the accepted formalism in probability theory, which you use in science and physics, implicitly or explicitly, is Kolmogorov, right? Formalization, which is kind of came, by the way, also from some idea expressed probably first. Again, I say probably first time, and this is exactly history I don't know, by Buffon, who found continuous version of first continuous probability model for defining of Peter, throwing baguette on the floor, yeah, and see how much it intersects the boundaries of the squares or something, right? This is famous analysis of idea of Buffon, who was not only biologist but also many other things. And but anyway, if I accept this point of view, there is some probability space, a specific or other measure on some space of configuration you have to invent, which is, of course, has no physical meaning, but you invent it, and physicists do it systematically, theoretical physicists. I don't know how experimental physicists do that. And then just see this as sample of data, and this is how you analyze it. And this is an issue. On the other hand, on the right-hand side, there is no apparent, right? This sample is there, but there is no way to make this law. And this is the problem from physicist's point of view, how to speak about biology. And so, but primitive thinking about biology depends first on our perception, visual perception. When you see life, you can't recognize it. And actually, not only ourselves, it's also true about animals. There are experiments with monkeys. It's about take 200 milliseconds on a screen. You know, you have a screen which you can to watch for this period of time and then decide whether it was animal or not. And a monkey do it fantastically well. Even with this sculpture of animal, they know it's not an animal. They wouldn't react. Sometimes they make mistake, but they recognize life. And we are very, very attuned to recognize life. And then we have illusion that we understand it. Like human faces, we kind of very good at recognizing, differentiating human faces. But if you look as a mathematician to understand it, and in particular to make a program, artificial program, distinguishing and identifying faces, then we realize we don't understand it, right? And so with biology, it took a long time before it was realized it's not understood. Of course, there was one point in biology which was questioned by many people before, or essentially contemporary with Buffon, is the nature of hereditary, how traits of parents go past to their children. What was the mechanism of that? And in a second, in this quotation which I had, if you come to the final one, so you can see, so Buffon realized that he couldn't understand life from position of mathematicians and physicists. And this position was not available before. There were no people of that style like him, or very few of them. Maybe Maupertuis, up to some extent, was, or maybe D'Alembert, who could make such a statement. And before that, people looking at life like children and saying, believing they understand it, looking at the simple picture. Or let me give another example. So you see on the picture, and you know what it is. A child understand it. I see. I'm sorry. Unfortunately, I don't have the list of pictures, so I have to. And I cannot go that fast here. It's very annoying. I cannot move it fast because it's usually in PDF. So I don't know. Okay, maybe I have to make it. Okay. It's much faster. And then we come back. No, where is that? Yeah, that's it. So you look at these pictures and you kind of understand here what happens. Yeah? It's very, 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 very simple for a child, and you can believe that you understand life, right? So, right? So, for example, so here you see the fox chasing a hare, and you perfectly know what happens and what the hare and why they move in this way. And you know, in ancient in Greece, philosophers would never ask ourselves why they move in this direction, why they move at all. They had a purpose, they move, but they couldn't understand when an arrow moves in the air. How could it move? And there was a big discussion between, you know, Democritus and Aristotle, and one was saying it just goes in vacuum, everything is fine, and Aristotle says no, there is no vacuum because nothing can't exist because nothing to start with. Looks absurd, but now we know he was right. And so, you know, to move, you have to interact with the with something, and we know it doesn't interact with some quantum field, and just not that we truly understand it, but both point of view acceptable, right? Anyway, it was a big mystery why objects move without purpose and without being effort. And here everybody kind of thought to understand it, yeah? By the way, about the rhinoceros, why are they crossing the road, by the way, no? You don't know? Because it's too long to go around. They realized that, yeah. Perfectly argue this way. Right? So, this is kind of a preamble to what I'm saying, just to convince you that it's hard to accept you don't understand biology. With physics, it was opposite. Yeah? Nobody understood physics, and then at some moment, starting from Aristotle was already articulating some physical laws. His laws were that speed is proportional to force. It's a perfect law in certain regime, small velocity and high viscosity, and people criticize him, but it was first apparently physical law articulated. It probably was before even Archimedes, historically, if I'm not mistaken, mechanical laws of Archimedes. But then, when Galileo, at the time of Galileo and just after him, and actually Buffon, most people, and it's still now, don't accept the laws of physics, even if they learn them, right? So a good example of that is Jules Verne's story about from the Earth to the Moon. He described how they were shooting, how they're flying, and make obvious mechanical mistake all the time. And they look obvious if you know physics, but when I read it as a boy, of course I would notice that. Yeah, then I read a book where explaining how many mistakes are there. And I'm pretty certain. But what I do know that there are experiments which show that people who studied physics at the university and still when it comes to real life, they don't accept the second law. They don't accept the law of inertia. It's absolutely counterintuitive. Everybody believes still now that heavy objects go down faster than low ones, the light one. It's absolutely universally, and again, you can make some little experiments and it is so, no matter how much you were taught. And there is a good reason for that. And there is a good reason for that, right? Because when you have something heavy goes on your head, you run away faster, right? Because you live for your life. Even if you don't have some intuition, you'll be dead with high probability. So you selected for the wrong perception of physics. So this is, but Buffon understood, on the other hand, now this level of physics we kind of believe we understand, at least we can manipulate and do that. Yet, also another very good example, I say in some moment, but demonstrate how poorly, say it's the second law is understood by population, when some people compare the law of evolution, like the fittest survive, with the second law of Newton. So he's saying, well, the law is also questionable, whether it's defined force as a ratio of mass to acceleration or something else. It's just fantastic non-understanding, yeah? Incredible, I mean, just because it's so much built on your mentality not to understand physics. But still, despite of that, physics is harder to learn, but once you learn it, you can understand it. One good example, which kind of the second law in saying it, comparing to fit to survive, which I may come again. So you know that if you know distance to the sun, you can evaluate, because it's difficult to determine. You know it, but it's non-trivial, by the way, you know, it's non-trivial to determine. Distance to the moon is easy, but to the sun, you cannot do it at home and at every moment. Yeah, it was a real task to do it. But anyway, granted that, you can evaluate the temperature descent of the sun, which is about 20 million centigrade, and you can do it by just from second law, derived from second law in mechanics. You know that? Okay, if you don't know that, you can fail. You can fail the entrance exam at the university, say in Russia, right? In mathematics. In mathematics, this is absolutely. You are supposed to understand that. This is exactly knows you understand the second law. You can know how to apply it, and in any way, it's everywhere. Right? It's a fantastically powerful thing, and its meaning also in many texts by non-physicists very much distorted. Because kind of physicists can understand it intuitively, don't care to explain those who understand. And some, of course, don't understand either. And very few people would explain it well. And it's explained somewhere, philosophically, what is the second law? And what's the significance of that? It's very different from the laws of biology, and we shall come to that. But anyway, so what is life? Yeah. So trying on all that, the typical formula being set, that it's combined complexity and regularity. And complexity can be mathematically formalizable concept in many ways. Right? The most common use is Kolmogorov complexity, which is give you the right track by itself completely useless, like all this mathematical thing, because emphasis of Kolmogorov complexity, like all this thing related to unsolvability, is going to go to infinity. But in physics and biology, there are limits. There are numbers, and you never go beyond certain numbers. And these numbers mathematically are very small. For mathematicians, like 10 to the 24 or 25, Avogadro number. And sometimes you take 10 to the power of this number when you look at number of the states of a kind of physical system, but this is already a kind of fantasy. That these things have no true physical meaning, but they're useful. By the way, this is amazingly, and there is a reason why it's useful, but certainly it doesn't apply beyond that. But then there is about regularity, and this is interesting. This is exactly in a kind of systematic sense. The system, life system, are both complex, which again, it's not so easy to say in both sense, right? Because it's not the point of the Kolmogorov complexity, which is relevant, but in a certain limited way. But what about regularity? So what we say in mathematical regularity often means symmetry, right? A regular n-gon, and some hint of symmetry. And then people say, oh, all crystals are also regular, or something. But regular, I believe, here means purely emotional. It's nice to look at. Because exactly your visual system adjusted to something which is alive. And there is some reason when you like to look at this. And there is some psychological mechanism which we don't understand why you like to look at symmetric objects. And it has something to do, I think, with information. And life specifically it has something pleasant to look at, because there are many intercorrelation in these pictures. So they're low, their complexity, but kind of on complexity appears on the next level. But anyway, this is one thing. And physically, so on the other hand, you cannot say it, yeah. People, physicists also can say it, but what physically, what does it mean? Nice to look at. It's not good. And one example, some point, kind of, when you want to distinguish that from life, was very well articulated by Chesterton. We see we got out of kind of by physicists, if you don't speak about Buffon, who was more on the biological side than physics. He knew mathematics. He was translating actually Newton foundation, understood mathematics pretty well in physics. But professional physicists who kind of was attracted attention to this physical perspective on life was Schrödinger, who gave lectures in Ireland in 43 or 45 or something. But before this was, of course, Max Delbruck, who was major contributor to his ideas coming from physics to biology. And so what's interesting about Delbruck, and this is about about some names of, I don't know whether it's accidental or not, of biologists, unlike mathematicians, were directly or indirectly involved into politics the other way. Say Delbruck, relative of Delbruck were fighting, and he was German. He immigrated from Germany on early stage, came to America, but his brothers, I think, were still in Germany, and they were at some moment arrested by Nazis, and some of them were executed by Nazis in 1944, and some of them were then executed by Russian next year, yeah, when the Russian took them from Germany, from the prison. So, and the same, we speak about some French biologists who also were in resistance and really had complicated accepting complexity of life at that time. I don't know any mathematician of that except Müller, who was just pro-Nazi or something, because on the academic level, mathematicians were usually aligned with the authorities, both in Germany or in Russia, many of them, yeah. So they were not that kind of concrete. It's not so kind of oriented this way. But this is people like Delbruck, the kind of the great mind and also great people by understanding, which is kind of an interesting combination. And so, and then, so just in the time of Darwin, who was emphasizing this idea that you have to find the principle of life on a physical basis. Right? So he was looking for that, and then Schrödinger kind of was saying more or less the same, that there must be some particular laws related to life, and none of this materialized, partly I think because concepts of law, I mean, confusing, because a language is so metaphorical, and so we say that physical processes abide physical laws, but don't abide by anything. Yeah, this is a metaphor taken from common usual practice and projected to physics, and it's no good, right? Like you have ideals in mathematics, but you don't apply phraseology used for human ideals. Yeah, and this was happening in this way. But so they were looking for kind of physical explanation of informational part of life. You see, the word information was not explicitly there, and so when you speak about that, you make stories, and actually very much think when you read textbooks in biology are just stories, and very much unlike how you describe physics, which is described by numbers. And again, there is a good reason why you explain physics so much encoded by numbers. Again, when you say it, it must be realized what kind of numbers. For example, you have a mass of something, so many grams. What does the number means? It's number in what sense? Yeah? But periodic number, elliptic number, what kind of number? What kind of number? It's not a number. Right? We don't know what it is. It's kind of a number. You can manipulate it up to some point, but only up to some point, and then not number anymore. Right? We can say it's approximate number, what means approximate. It's not a mathematical concept. So this is an interesting point. Yeah? When you apply physics, you immediately go outside of mathematics. You use the same words, but in a slightly different way. Right? And physicists really think differently from ourselves, and very efficiently for their purposes, but it doesn't apply to biology. So one of the points following Schrödinger is to understand biology, realizing that you cannot do it from the way you understand physics mathematically. It might be a really different way to thinking. It's not that you have different laws, but a different way manipulating with the symbols, or logical or conceptual symbols with words, which are symbols. In particular, vocabulary of life is much greater than vocabulary of physics. In physics, you have few basic observables, like mass, energy, action, maybe half a dozen of them, and then you manipulate with this. And they're numerical for some mysterious reason, because mass additive, entropy is kind of semi-additive, and the same applies to energy. And forces also kind of additive in vectorial sense. And therefore mathematics immediately enters with all fantastic kind of consequences, because you see the existence of real number, from physical perspective, if you think there is a structure in the invariant properties, you see there are so many it's highly overdetermined. So you would expect they don't exist. So the whole fact of existence of this framework of numbers for physics is as incomprehensible as its applicability to physics, which is if a scientist look at such structures, of course, it can't exist, like of finite fields. Of course, for large, there will be no large prime for finite fields. If you see how many conditions must satisfy, or at least the density of these possibilities would incredibly low, much less than density of primes. Okay, so this about problems. Now, but what we want to do with this? Yeah, so this problem is complexity. Yeah, something relevant. Yeah, here is the standard picture now of life. So the last, by the way, quotation which I made was by Jacob, who was exactly the person who was in resistance. He was actually fighting with British against Nazis, and he died rather recently, 20, 30 years ago, recently on my time scale. And I will talk about one of his contribution to biology, and he had emphasized that information must come in there, and so I think it is our starting point, that we want to describe life in the language which incorporates matter, energy, and information. And it's not information of Shannon. Information of Shannon, like usual mathematics and usual physics. It goes in numbers, yeah? You have entropy, it's a number, you manipulate with this number and just perfect. And here it is not that simple. We don't know how to define it. And the only, I think, attempt to define it is stupid. There's no chance. You have to see how to use it and try to do it systematically as a mathematician, accepting. So the point I have, you accept all words biologists use, but try to think about them in maximally general terms, and eventually to find other kind of worlds where the same thing apply. And this is a following idea of thesis said by Poincaré, that mathematics is an art to give the same name to different things. But you have to find these different things where we have this combination, matter, energy, information. And matter and energy here is secondary, so to speak. On one hand, of course, information depends on that. On the other hand, it's a minus. All structure come from information. And you may forget about matter, energy replaced by something else, not fully to forget it. If you fully forget it, you have Shannon information. It's kind of, from this perspective, something very simple. But there may be some background which has features comparable to matter and energy. And matter and energy is when you can numerical formalism, and it may have very different properties from what in common physics is, but which support this information, related to this information in a very, sophisticated way from mathematical point of view. And this is what we want to do, try to see that. But for that, you have to see, of course, first what we want to apply it to. So, yeah, just maybe again one remark because it's written here. So what's the problem with physics? Why physicists in principle cannot speak about biology? It's not that there are some laws which kind of being not satisfied, being broken, but there is no expression which would allow a physicist to speak about life. And some start with a rather naive example. If you have, as you know, as was said by Einstein, that if there is a single experiment which contradicts your theory, forget the theory, and then start anew. But it's, of course, not exactly, because the question is how you interpret this experiment. Right? There is a Galileo law, everything, all objects, more or less with the same weight and density, go down with the same velocity with minor correction for the other resistance. However, if you take a bird, it flies, it doesn't fall down. How we can reconcile it physically? How you say it? What? So what's wrong with physics? You cannot say it's alive. There is nobody knows what it means to be alive. And there are several solutions, by the way. I thought I was doing physicists immediately say, oh, well, try vacuum. Well, we don't speak about vacuum. Secondly, in vacuum, you can imagine some device, some mechanical device which do something like that. You have some propulsion system which react and on the environment and fly away or to do something else. So there are one general phenomenon that when you say something about a physical law and say all objects, when all means not means all. When you say all, it is, again, metaphor of something. In mathematics, all is a symbol, logical symbol with which you manipulate, which you may interpret in some way in a set theory. But in physics, this all means most probable or generic. Generic system fall down, and biological system highly non-generic from a certain point of view. It's one way to say it. And this kind of universal principle. And this is Schrödinger is in his book about what is life. And I will give, when I put this on the web, not what is here, but what I wrote more systematically, when there are quotations for Schrödinger, and he emphasizes that physical object, what we observe is not what is there, really there, but what is most probable. Right? Everything which you observe in the macroscopic world is just manifestation of some generic phenomena, and there are some mathematical mechanism why force them to be more or less the same everywhere, like the law of large numbers. Right? If you look at a random sequence, and you see 0 and 1s, yes, it's random and it's everywhere kind of different, and there is no pattern. However, if you look averages on a big segment, almost all these averages will be almost the same. See? Almost the same. So it is this big kind of emphasis was articulated by computer scientists. They have this PAC theory, probably approximately correct. And they can make big fuss out of that. But this is a basic principle of everywhere. Things in physics are probably approximately correct. But the question is, what is the error? And it is one thing. Another very simple one is what was articulated, this law actually by, at least where I saw it for the first time, by Chesterton about 25 or 30 years prior to Schrödinger. And he said that the difference between dead dog and a live dog, that a live dog may go against the stream. In the stream, even dead dog will go and move by wave. By going against the stream, that's characteristic of life. And in particular, birds can go against the stream of gravity, but more fundamental process where our life goes against the stream, it's the stream of how to say this, because everything, as physicists say, I repeat this, but though I don't like it, that entropy increases. There is averaging process, average situation, and they go to more symmetric, and which is equilibrium. This increase in entropy means increased symmetrization, stochastic symmetrization, right? And our organism goes all the time against it. So the stream which moves, leaving down, and we keep up. Therefore, if you stop going up for a moment, and then you go a little bit down by the stream, and then you cannot go back, right? So it's all the time there is a stream you fight against. Of course, this you fed up by free energy. So this is a problem. This is just objection to physicists. However, like people like Delbruck, they fundamentally contributed to physics, and there was kind of famous experiment, Delbruck and Luria, when they kind of confirm, which is said even now sometimes, that it is a Darwinian point of view on evolution versus Lamarckian, that acquired traits are not being inherited, and then they just come spontaneously. And it's wrong on very many accounts, because first it had nothing to do with Darwin. Darwin actually was propagating this idea very strongly, and was criticized by Weismann, who actually first articulated this idea for good reason. Secondly, it depends on interpretation of a particular experiment, and thirdly, we know it's just wrong. Exactly, the experiment was not sufficiently how to say. In a second, I explained what was wrong with this experiment. It was a typical physical generic experiment. Generically, it is so. Experiment shows something is true generically, but life is not about generic. Life about exceptions from this generic. And phenomena which you know now, it calls CRISPR. CRISPR, we know in bacteria there is something which was in principle kind of contradicting to this experiment, right? Or by this great experiment. Well, it was a great experiment, very interesting, with some mathematics involved, and of these two people. But I think it was invented. My feeling, it was actually invented by Luria, who also had mathematical education, and then Delbruck just mathematically justifies slightly better. We come to that. This is a kind of nice piece of science, though it happened to be not exactly adequate. No, so what comes next? Yeah, here is a typical what biology, the picture of these many factors involving in life. The key word they like to say, and our purpose to understand them. This far from equilibrium was emphasized by Schrödinger, but this I found rather idiotic. Nothing is in equilibrium. We never see anything in equilibrium. All systems out of equilibrium instead we have complete death, future universe in quadrillion years from now will be in equilibrium, if ever. So, so life is kind of pronouncedly out of equilibrium. We think about that in this term, but it's nothing special about life, though it's always emphasized by people repeating who don't know physics and repeat after Schrödinger. This is my impression. And then there is Darwinian evolution. Why it's called Darwinian? Again, Darwinian doesn't mean it was invented by Darwin. It's like, and it's never given the right names, but still all these words, whatever they are, needs to be understood in mathematical terms. So I'm saying there are lots of words in biology. Another set of pictures here this is the instance when certain structure appears. This is the structure of the trees, which are more essential, quite essential in biology, is trees. Albeit it may be a tree here, here you have the tree also, here you have tree structure in alive situation, but also in here. So a tree will look very much like somebody alive, yeah? And there is some common phenomena in non-alive, in material, kind of pure material worlds, which carries no information. So I think that, again, it's justly emphasized by Jacob, is mixture of information and matter and energy, and the way how they mix. Right? It's a very incredible logical mix, and we don't exactly understand how to deal with this. So I will give some examples of that, and at some point. So what comes next? Yes, here is topics we want to discuss. So it's supposed to be the first lecture, but probably will take slightly longer. Let me see how my time goes. Okay. It's not so bad so far. So now we want to again emphasize and this kind of realize that we, in principle, don't understand that life from physicist's point of view. If you take our science of numbers, we don't understand what happens with the life system, and we don't have other kind of reference point, except for physics. Because in some sense, indeed, we organisms, whatever they are, physical system and they're run by some kind of laws of physics. But it's kind of, but it's again, these are metaphors which are misused at this point. Right? Everybody says that, but it's a metaphoric thing. Yeah, there are mathematical model, and then there are which you apply to physics, and then you know how to fit this model in the real world. I don't know. Physicists know, right? And they do it sometimes right and sometimes wrong. When it comes to physics, to biology, they make mistake systematically. Right? The famous example is Fred Hoyle, who was great kind of physicist, astrophysicist, one of the greatest kind of physicists of the century, and he gave some very good physical reason why evolution is impossible, and that life cannot come from non-life, it's absolutely improbable, and made some computation, and we had typical physical reasoning, and his conclusion was there is no life, and, well, but what was physical, made this computation, you use unconsciously the physicists were to do that. Himself, he was famous, a very remarkable thing, he discovered the origin of high elements on Earth in particular, right? Because there is in the sun and it's around us, what you see is basically hydrogen, helium, a little bit of lithium, and that's it. There is no carbon in particular. And he realized how carbon could come up by fusion in supernovas, because for that the temperature of the sun 20 million centigrade, no good. It's not high enough. You need about 1 billion to have oxygen, and this happened in supernovas. And he kind of developed the theory, and it was not just something. He predicted some particular nuclear reaction by which we can have carbon. And it was experimentally verified on Earth. This kind of quite remarkable discovery of his remarkable contribution there. So this is, and this was, he was partly motivated by understanding how life could appear, because there is a carbon, and we depend on carbon chemistry. And again, we don't know if there is other chemistry which can support life. It's an interesting issue. But if we actually indeed ashes of supernovas here, and on the other hand, the life was probably partly damaged by nearby supernovas. It's an interesting picture of the world. But anyway, now, so what we can say about, so our point is to say life, we have to look at, on one hand, at some particular phenomena and structures. On the other hand, trying to speak about them in generic terms, hopefully it will become mathematical. And this, of course, I haven't achieved, but this is my goal. Now, very simple example, why it's impossible. If you look at your skeleton, human skeleton has about 200 bones, which kind of, you know, goes down with age. You are born with, I think, about 200, and some of them then join together. And there are, well, so many joints. And you know, so joints are rather big, and they have to fit with the size of 1 millimeter, so it's 1/10%. And then it's a huge amount of information, right? How it was presented there, how it was done. So you have one joint and another joint, and they had to be made to fit each other, and to fit pretty well. Not to say that they must be have particular, but must be round. And you know, there are two types of joints. Some joints are not movable, it's like your skull, yeah? Some pieces have rather random picture, they join. And then, of course, there are your moving joints. And there are two types of joints, like in your knee, it only has 1 degree of freedom, or in your hip, on your shoulder, it has 3 degrees of freedom, right? And there is no joint with 2 degrees of freedom. Why? Mathematician. If you have a surface, Riemannian surface, with 2 degrees of freedom, you have 3 degrees of freedom, mathematically. And these 3 might be either spherical or Euclidean or hyperbolic plane. Right? Well, our joints are not hyperbolic, and those which are cylindrical, they are intrinsically Euclidean, or there are balls in here, right? Except, look at this, it's 3 degrees of freedom. How come? Contradiction in mathematics? This is exactly the problem with biology. Yeah? So you can make this, actually there are other kind of interesting example of similar contradiction. I tell you a story in a second. And so what the answer? So you don't know anatomy, yeah? Probably, none of you. Huh? There are 2 bones here. This is part of it made with 2 bones. So there are 2 joints here. And this is how it happens. It's one joint moves with respect to another. But these are, of course, rotational joints, exactly as your knee. But this is separated in 2 bones. So that's the problem. Everything you think you understand something, and biology says, oh, well, there is something else. And the story was about DNA replication. That I will come to that in a meanwhile, when mathematicians also make some kind of observation, found out that something must be wrong. Indeed, they found some contradiction, but of course, people who kind of first conjectured the way replication goes, Watson and Crick, they perfectly knew about that. You were writing that, right? So if something is kind of tricky, when you do something in biology, the thing cannot fit perfectly. But if something fits already very nice, you may be sure you on something, on one hand. On the other hand, in mathematics, I don't know what about physics, I think probably it's not so. If you have a good idea, there is a chance, maybe at least 50% it works out true. But in biology, I was told by people, actually by physicists, if you have a very good idea, really brilliant idea, there is maybe 0.5% of a chance it works true. And it's very good. Yeah, because usually nothing works. Yeah? Because always there is more and more. One remarkable example to which maybe I come, one brilliant idea and which kind of amazingly works with PCR. So this purely mathematical idea, very logical idea by Mullis, who invented that. And it worked, but it was hard work. Actually, sometimes people say, oh, well, he just done it and then it worked. Well, actually, it was take years to implement it. And it was because, yes, but sometimes it does work. But this was really a super brilliant idea. So that's the attraction of biology for mathematicians. There are some ideas really fantastically beautiful, and amazingly they work. Which all this chaos which biology exists, they work. So this about the bones. By the way, how it happened? So where this information kept? Of course, now a posteriori, you know, this is DNA, and there is this digital information, but still it's a lot of things you have to know where and how some position, little part of the body, molecule where they are positioned. It's certainly huge, by far more than can contain a single molecule. But then again, there is solution. So we can say on the basis of that, say, well, life is impossible, something super laws which govern it. But then there is solution, of course, how it's done, how you achieve the perfection that one join matches another. So I say, oh, it's for selection. First you make square joint, it didn't work. Then you make, rectangular joints, it didn't work. And evolution was selecting from this, but it's nonsense, of course. Yeah. Nature was not going this way. But of course, if you look at the morphogenesis of joints, the whole volumes written about that, it's a fantastically complicated process. And in my understanding, of course, and the major process which achieved this is that first thing make more or less solid, of course without much calcium there, but then there's a film between this being formed, and then the film disappears, they die. This apoptosis is correctly basic process. You create cell and then cell dies, and this is how it works. It's very many things about like that. You have auxiliary structure, and then the structure disappears, and you don't know what the structure is. And this, of course, fundamental mathematical problem, which is manifested in this P and P problem, right? When you have something cancel off. And the same, by the way, everywhere in mathematics, kind of complicated construction mathematics, something cancels off. And life uses this all the time. So it's very much similar to how mathematics works on large scale. So this is how joints are being made. Because I look superficially, of course, on these articles. It's really fun to read them, but it's a lot of information which you hardly can. Now, the words. So these words about information. And so, so what is about information? It is like what Jacob saw, it's a flow, this triple flow, and this information coupled to the flow, energy and matter. And so what is this information? So this information, not abstractly information over Shannon, but this information first, it is physically represented by covalent writing on the periodic molecules. You see, the background bone of DNA is a really periodic, it's usual polymer. And then to this you attach some letters, which are the basis. And this information is written in this digital, perfectly just digital way, on the periodic background, and so it makes sense. But then this information about something, and this is about something, how to make the cell to run, right? It says you have to force it, and the rules is kind of like physical laws which determine how to do that. And this implemented by physical properties of this very DNA, which contains information about itself. And this was articulated very well by von Neumann in his model of artificial self-reproducing systems, to which we shall return. It's again mathematics which has not been concluded, in my view. It was everything was done very closely following von Neumann, but there is much more which you can say and do in this direction. And so what I want to say, yeah. Here is a basic expressions involved into information, and we have to make mathematical sense of them. For example, what I said, information about something, right? So it's kind of a knowledge about what will happen. So which is in the key words here is control and regulation. And again, they have no kind of place in mathematics per se or in physics. They have to invent how to use them. Again, not that we have ascribed some extra meaning. We know what has happened there, but we have to develop language where they fit as an expression in this language, right? And this language will be different from a usual mathematical language because there will be much more internal kind of terms, and the interrelation will be taken from experiments, so to speak. Yeah? It's very, very kind of tricky, so it may be self-contradictory, and will be kind of quite normal because the logic of this life is self-referential. And this one, which makes it very hard to formalize, because there is information written in this DNA is about itself, and we know the moment you say it, you run into logical contradictions. But it's okay. You have to. Otherwise, we wouldn't be here. And this is the same partly what the problem with intelligence. Yeah, it's also self-contradictory. And if it were perfect, like computerized, like Penrose explained, it wouldn't work. But not for some quantum reason, just logic is different. Yeah. The way we implement mathematics in some way, you make you very often confuse metaphors and the reality. So here these little things. And so this is our problem. And now, well, just something about life. So now the next hour will be kind of elementary tutorial about basic things about life, actually of molecular and cellular biology, just some rudimentary. So if you're a biologist, you'll be bored by that. Yeah. Yeah. This is I'm citing Wittgenstein. What is the meaning of a bird? And this applies to mathematics. And in linguistics, yeah, it's not everybody accepts it, but it's in a way the only way to think about meaning of words is emphasized actually by Harris, and that there is no external meaning of words. If you broadly understand the language, it's only internal, and external is just the way to. And this internal, what's good about this point of view of internal, this is what you can imitate on computer programs. Everything else is just in your head. Now, what are basic units of life, right? So, it doesn't quite fit. So the point which we do have about life, again, on the formal level, but life consists, kind of, whatever it is, the basic life entities are isolated, and there are only two basic types, which is kind of remarkable, very few, and they're cells and organisms. And they're really autonomous. And they kind of really separated. They interact, but they were highly autonomous. And there are kind of physical and chemical processes running in them, metabolism, what is called, and there are information processes inside of them. And their major purpose is propagation of information, right? So, and when you say information, immediately you introduce words which become teleological. You introduce concepts of a purpose. And sometimes biologists kind of hate speaking about that, and say in particular when Darwin explained evolution, kind of avoiding idea of purpose, and it was hailed by physicists, like in particular by Boltzmann, who was saying, well, the 19th century will be called the age of Darwin because he found mechanistic explanation of life. Mechanistic, and you know, Boltzmann himself found mechanistic explanation, mechanics of particles, plus probability explanation of behavior of matter, at least of gases, right? And so, but this kind of interesting that I always try to imagine what Boltzmann said if he also read an article by Mendel, which appeared a couple of years after the Darwin's book on evolution by selection, because it was something kind of neither mechanistic, but certainly by far more amazing, that there was some fantastic regularity in statistics, and this was, I think, Boltzmann would be completely overwhelmed by that, yeah. Which, unlike biologists who basically couldn't understand what was there. But biologists at the time, when some on men were some numbers, it was fantastic, kind of, in my view, ignorance of these people. They were great people, some of them were really great scientists of the time, but they couldn't appreciate this idea because it was so new. It was second, actually. There were two big discoveries in biology. You know, second one was Mendel, and was the first. By the way, he was not a biologist. And the first discovery was not only not done by biologists. Discovery, people discovered something they never knew, never suspected, right? And there is third one yet to come, I guess. Yeah? Third one is still there. And this was by whom? It was Leeuwenhoek. He discovered microscopic life. Now we know this is the essence. If you understand life, now you always speak about on the level of bacteria and cells. This is from where understanding starts, and then you build on. But this was discovered by Leeuwenhoek, who was not a biologist. Yeah, he was a really great fellow, and people most of the time people didn't believe what he was doing. It was too good because he has a very good microscope. And somebody who was doing in parallel work and who discovered cell. Who discovered cell? You know, I don't know. It was Robert Hooke, you know, this guy who attributed this law of mechanics and many other things. But he discovered cell, and he gave the word cell. It's his word. He discovered this in trees, yeah, and in plants where they're much bigger than, they're often bigger than animal cells. But Leeuwenhoek, and he was actually criticizing Leeuwenhoek because Hooke was using microscope with 2 lenses, which is certainly more efficient. But Leeuwenhoek using only 1 lens. And nobody believed it would be possible, but he was making fantastically good lenses. And nobody understood at the time how he was doing that. And it was understood in 1950-something. People realized how he was doing that, how he making these lenses. Because he was managed to make drops of a liquid glass and put them in some positions that he certainly was very good observer. And he discovered basic organism, microscopic organism. This was really a shift from world. Before, no discoveries. People were just looking around, you know, like there's a cow, there is this or that. And there was nothing fundamentally. I think discovered something. And anatomy and physiology, of course, was done even in ancient time and a little bit anatomy, but there was kind of nothing so radical as new kind of organisms. And then it was found by Mendel that there is some phenomenon, apparently on molecular level, of related to hereditary, and the person who already had similar ideas was, again, not a biologist, but it was Maupertuis, who was known for Maupertuis, you know, least action principle. And he was on the same track, but he hadn't gone as far as Mendel. So, of course, and Mendel, so Maupertuis analyzing phenomena when people have 6 fingers and how it goes in the families, and he was trying to see the patterns. And he was close to Mendelian ideas and of gene. I don't know how much it was articulated actually by Mendel, kind of idea of gene, but certainly he understood. He was mathematically educated. He was physicist by education, actually, Mendel, which is, and he had extremely passionate. He was thousands of experiments with bees and see how certain features appears when you interbreed them. And this is kind of remarkable work he's done, which was not appreciated. And it was rediscovered by how people rediscover this. So he wrote a paper and nobody read it. But then, so what happens? About 30 years afterwards, 3 groups of people made similar discoveries. And so very much annoyed seeing somebody else discover what they did. And so some of them, just to feel better, he looked in the literature, found, oh, well done by Mendel. So it was not so. If you prove some theorem, somebody a great theorem, and somebody else proved it, you will be much happier know it was done by somebody 30 years ago, right? You feel somewhat better. So this was exactly how by Mendel we know about Mendel. If it was somebody, one person who would discover this, nobody would knew about Mendel. It was one little article, and nobody read it, though it was in the library of Darwin. But Darwin was far from understanding it. In principle, Darwin had already some philosophy which would preclude him to accept these ideas, yeah, of continuous information, of continuity of life. So our point is try to formalize and describe basic phenomena in life in these terms: matter, energy, and information. And when you combine matter and information, it's amazingly many things come around. Because you say that matter carries information, matter follows the rule given by this information, and this happens on many stages. And some people, especially when it comes to the recent time, say, well, it's just too simple. And now when we know more about cell, especially regulation of gene regulation in eukaryotes and organism, which is RNA regulation, which came up in the last decades, so this is something else. It's not so simple in life, and particularly there is a nice book by Philip Ball, who's a hugely educated person, and he wrote this book about how life works, and he says kind of things, and I think some biologists would agree with him that living system are production of meaning, and he very much emphasizes that. And I just think it's kind of rather strange. Yeah? I think it's completely kind of not empty talk, because we don't understand how information is distributed and how it's being communicated on the level on certain processes coming for higher organisms, multicellular or eukaryotic organism. And it's already, this problem already before regulation by RNA, it appeared when people, well, realized that genes are not as simple as they are not one piece but many. Okay, we shall come to that, yeah. So in order to make any kind of interesting mathematical description, you have to learn what is there. So how information being encoded, what this information is in real cases everywhere in biology, but sometimes it is hidden because you see information, something which you don't see, right? If you look from physical point of view, if you look at a cow, you may not think about it made out of atoms, and but you have some information about the cow, the whole structure of the behavior, which is kind of informative. It tells you much about the cow. If now you take physical point of view, and this is you go in another level, and then it's a bunch of atoms, and how the hell you can say anything else about cow, right? It says, in this language, you just, certainly, you can go on the molecular level and saying it produced milk, but you don't know why the hell, how it happened, it came to this stage. And, Feynman, I think, was saying at some point that you just know to understand anything, you have to know the world we made atom, how atom interacts, you explain anything, including life. And it is, certainly, the word explain is, well, of course, we are made of atoms, but it tells as little about life as about kind of painting. The chemistry of the paints doesn't tell you anything about painting. Yeah, it's much more special to the context. It's very much contextual. Okay, so now we shall turn to something more concrete, but now we make little interaction. Yeah. So from this moment on, now from what follows will be little tutorial on cellular biology, what we know about cells and molecules in it, because they will enter, at least terminologically, they must enter mathematical language. So let's make 10 minutes break. So one kind of remarkable thing is that there are only two fundamental units of life, and these are cell and organisms, and they unit, and then each of them appears in many, almost identical copies. And there's nothing like that appears in physics. So you don't have to go further. You have a rather elaborate thing, quasi-random, complex stuff, essentially looking like random, and then it appears in very many copies. And so especially if you look at the bacteria, and the kind of interesting kind of numerical phenomenon that the number of atoms in a bacteria is about 10 to the 12, is smaller than the number of bacteria in usually community of bacteria. If you look at the number of bacteria in your guts, probably even of E. coli, maybe not the only one, maybe particular E. coli will be slightly less, but if you take little kind of pond where you may find more copies of a particular bacterium than the number of atoms in this bacterium. And this is not true already when you go to eukaryotic cells, or not so much to organism. Of course, it's amazing that you have almost identical 8 billion skeleton like ourselves across the world, also absolutely physically impossible situation. How it can happen? That you have essentially a random pattern and appears many times. If you have a random pattern, you come to a new world and see a random pattern appears here and somewhere else, 10 kilometers away, it must be trace of life. Just no physical process can do that. Of course, templating you can imagine, but theoretically, but nobody ever seen that. Of course, molecules themselves, they are the simple structures, or atoms, even so, they appears in many copies. And but this is related, and there are relatively few copies. And I think it's related to the fact that intermolecular interaction in organisms much weaker than energy interaction between atom and the molecule. They actually disappeared. Right. So there is this actually on the molecular level, on the atomic level, there are several kind of numerical phenomena which you have to keep track of. And this is one of them. How much copies and how much internal elements are in some particular unit. And unit are organisms, and they're very well shaped. Yeah? We are not connected physically. We are all distinct, and we are similar. And that, again, this is one of the characteristics of life, and for mathematicians it's very pleasant. Yeah? Mathematician can of understand that. Also, when we say complexity, maybe I say one word about complexity. So first, let me remind, what is Kolmogorov complexity? When you describe something by program which can generate this something, and this is the length of the program which is needed to generate this something. But the program may be enormously complicated. Program may run very long. It's probably not one thing which is disregarded by this complexity. And secondly, finding this program may be also very difficult. The program may be short, maybe 10 pages, right? But how you find these 10 pages, right? So this may be the whole life on the Earth is run by this kind of program. And it will be it's conceivable that all this program takes, you know, just 1 page, 2 pages, maybe a very short program. Just what you have, how it works. And then there are some parameters, which is specific parameter where life emerged, but we cannot find it because we're faced with this situation. The number of possible programs with so many symbols may be still too large for us to find. Right? It's an aspect which is reflecting the P and NP problem. Yeah, you know, finding because something has cancelled in the course of this writing of this program, and this cancellation. How cancellation happens is an essential part of understanding life, where things being cancelled. Again, this mathematical phenomena, it does happen there, but precise role of this is not always clear. One of the typical instances when it happens on a large scale and absolutely crucial in life is in the acquired immune response. Yeah, that you learn how to react to pathogens and to invaders, and the way it was being prepared was by killing most of what has been done. So you produce all possible kind of antibodies, and then you kill huge amount of them which can hurt yourself, right? So this cancellation is there. It's always apparently in multicellular organism everywhere. This is a mathematical phenomenon which in this context yet to be, of course, understood. Now, so these basic units are cells, and now there are pictures. I want to show you some pictures of cells. First is so what where? Yeah, this is a simple picture of a mosque which studied bacterium which live in your guts, and so purely mechanically, geometrically, this is the size. It's a scale of 1 micron, and this is a characteristic size of life. So it's a 1,000th to the nanoscale, where molecules have 1 nanometer size. And it has here described like that. It has a membrane, which I believe about 3 nanometers. And all cells have their membrane about 3 nanometers. And membrane, so let me look more, show you better pictures of the cell. Of course, lots of pictures here. It's impossible to describe them, of course, better than that. So shall we go to the bottom? Yeah, here is a picture of membrane. Probably works well to enlarge it. Now, membrane is, again, mathematically fascinating object, if you think about that. So there are all these proteins sitting there which determines its particular properties, but before you go to this high level, protein just is made of this bilipid layer. You see there is vertical molecule in 2 layers, which make the membrane and the thickness about, I think, 3 nanometers. If my understanding, it's roughly the same ratio to the area to the volume as for the airplanes. Yeah, Boeings have the same relative thickness of the outer surface. But so what keeps it together? So forget about this protein, which is, so the function of membrane, of course, to isolate cells. Of course, there are some entities like where these cells merge together and sometimes become long. But as everything in biology, of course, if something, as biologists say, is always true means 80%. Even 60% already good, yeah? Because what they describe is so incredible, so even there are many exceptions, it's still fine. But so what keeps it together mathematically? What's mathematical problem? So I have this molecule, the bilipid molecules, they're pretty small. Well, just each of them is about 1 nanometer, they're glued together, the double, by bilipid layer. And they make kind of these rather round shapes. What keeps them together? What is the force which keeps them together? And the point is that there is no physical attraction between them. They are not attracted one to another, right? So what keeps them is that they're not attracted, but they're better attracted to themselves than they would be attracted to water molecules, because they're not polarized. Water molecules polarized, they stick to each other, but they don't want to stick here, and therefore if you write it together, it is just bottom of some Boltzmann distribution, and you look at the energy, interaction energy between molecules, between them, where there is no interaction, and how interact water molecules, you achieve the minimum in this way, right? Because this maximizes attraction molecule because being, otherwise they would more interfere, individual molecule of bilipid more interfere with water molecule and don't make them attract very much one to another. People say it's entropic effect, but of course it's not really entropic. It's energy mixed with entropy, right? This you maximize the entropy or minimize free energy of the system. And this, of course, depends on the temperature. If you start heating that, up to some point, this molecule run away. And when you cool them, they again make this nice shape. And this shape satisfies certain partial differential equations. They believed, I don't know how, it's intuitively what you expect, whether it's true or not, it is another matter, that they minimize integrated squared curvature of these surfaces, right? Per given area and given volume they encompass. And apparently, if you look at erythrocytes, we have this by convex shape. They are extremal for that, but which is mathematical conjecture. Okay, it's not proven, but this is one known that if you have something having the rotational symmetry, it will have this roughly this shape. This was, I think, was easy to compute, and people done that, and who done that believe they've proved it always so, but for mathematicians this is no. So it's again extremely interesting shape. What's remarkable, it has this tendency to self-assemble under certain condition without interference of extra proteins, which is of course not true when there are all the bunch of these proteins, yeah. But however, there is tendency, and this was one of the major ingredients probably of appearance of life on Earth, that they contained kind of to allow high concentration of certain molecules, so the anabiosis production of more complicated structure was possible, right? Because if you just think about these ideas of primitive soup, which was suggested by Aparin and Halden somewhat later, it's certainly inconsistent with the tendency of things being diluted easily, and presence of the bilipid is crucial. This probably was the main step of life, namely this membrane created separation of different parts, and everywhere in the cell, inside of eukaryotic cell, and partly in prokaryotic. So there are two types of complexity of the cell, and actually the picture of cells. I didn't show this picture. Now I want to show it. Very good picture from standard textbooks. Well, here it is. Which give you an idea of the size of the cell and their level of complexity. This is, I have to enlarge it. This is our kind of cell, and here is small bacterium, and then there is yeast cell, and there are this kind of fundamental distinction between, again, it's terminology. There is all reason to expect this universal phenomena, this distinction. There are eukaryotic and prokaryotic cells. And so prokaryotic cells have two features. Their size is exactly such that their ingredients is smaller than the number of them in the community, and for eukaryotic one is different. And actually separation between them time-wise in evolution 2 billion years. And this, I think, may be related to this numerology. Kind of.
Excuse me, can you repeat the numerology?
I'm saying that if you look at bacteria, and then the number of atoms in a bacteria is smaller than the number of kind of basic community of bacteria. Therefore, it makes life possible stochastically. It means that if you have stable condition, but on the very long scale of time, most of the time you will have the bacterium. But if it were slightly bigger, say, like 1,000 times volume was big, it would be not true. It would be, its existence would be very improbable. This silicon computation is just very trivial because you see how many combinations of atoms, how many bacteria, exponential replication, and then this constant match. And they said that you couldn't have, the first organisms must have been small, must be of order of bacteria. They couldn't, principle could be large. But if they're much smaller, it's also unclear how they could exist. For all we know, the structure of the living, we cannot imagine something easier. But this is definite phenomenon. And how much repeated, of course, the bigger and bigger organism, in principle, you cannot have so many. And of course, materially, you cannot have so many, you don't have enough material, but also informationally speaking, you see? And this is how you have to use, try to imagine, to count information involved and probability of its creation and to see how it works. Another point you can make in this respect. So if you had kind of your information, everything in your body could have been reproduced and recorded on the level of on the geometric level, then evolution should take about quadrillion of years on the rate which we know mutation take place. But because it's written on DNA, and so instead of quadrillion whatever cells we have, even more than that, we have more atoms, you have about trillions of cells and quadrillions of atoms, you have relatively few essential ingredients and information. Of course, your genome about 2 billion bits, but most of them probably is material, so it probably reduces by a factor of 10, and therefore the number of steps going from point to point is log of this number, and it's compatible with knowing rate of evolution with the time involved into evolution. Very roughly, of course, yeah. But this was intuition of Darwin when he argued with, of course, he had no basis to know that, but this was kind of the idea that still there are so many features, and therefore to produce evolution you need long time. It was counted in billions of years rather than in millions, as you know, Kelvin Thomson believed, and actually proved it mathematically. You know that he proved mathematically and argued with Darwin that the age of Earth was below 100 million years. And his estimate was probably about 20 million years. And his argument was the rate of cooling of Earth. So originally it was hot and then losing heat, and he looked at the heat equation, analyzed this heat equation, and the data of the gradient of the heat, where the measurements was done by his time, and came to this conclusion. But he was wrong, and people believe he was wrong for wrong reason. Yeah? This way they believe, what he didn't take account, this radiation in Earth and everything. However, that's a very, again, interesting story, where the story came that he was wrong for this reason. First, it's, of course, created by people who don't know the physics. Right? And I must admit myself, when I read it, I could never understand. So I read what mistake was. But how this kind of story appeared. When radioactivity was discovered, and Rutherford was giving a lecture, and old Thomson was sitting there, and he wanted to say something pleasant to him. And he said, we discovered radioactivity, but you predicted this, but you said there is an incompatible thing with the cooling of Earth and then its age and so on, you can say that you are predictor of radioactivity. And Thomson was very happy. But a component of the radioactivity is a minor factor, maybe doubled. It doesn't change radically. The mistake he made, and it was known already in his time, but he disregarded. There was some young man who explained that, and he said, well, you didn't take into account convection of the magma. And when there is convection, the heat goes, of course, much faster, but not slower. And then, of course, I remember I read it was what the hell. If the convection would cool even faster, so the age of the Earth would be even smaller, right? But what was the point? He used a kind of simple thing, because if you just forget about convection or anything, and you think how long the Earth should have been cooling from, so how long it takes? It was at some moment it was, say, 1,000 centigrade everywhere, or say at the core. How long it will take to cool? About quadrillion years. Because heat goes very, very slowly, and the time to pass some distance goes like square root of this. This is a kind of basic square root of probability theory, right? A random walk, the length of a random walk of n steps has the length square root of n. So, I mean, of course, this is an interesting point, because this is written by physicists and then written by somebody. And then I read by physicists and said, well, everything is because physicists would never say that. For them it's so obvious. And what was doing, well, and the convection makes is just all this applications just of heat equation. And of course, he knew everything, of course, that. Mathematicians forget it. They write this heat equation, but forget that heat equation corresponds to the square root. Actually, myself, when I spoke to other mathematicians, people don't realize it. Exactly, we learn things, but we don't understand what we learn because we don't have enough examples in our head. There are billions and billions of things we have to try what we learn. And this convection changes the gradient, and the gradient here observing by actual measurement was forced by this convection. And so all computation, I still don't exactly understand the subtlety of all this computation, but anyway, it's something is worthwhile understanding how easy to make mistake. But that's incredible that Darwin, he was certainly not as smart as Thomson, still was right, and Thomson was completely wrong. And because exactly you don't apply, he knew all this mathematics, and Darwin exactly was saying, okay, I cannot argue about mathematics, but how I know you apply it correctly. Right? You make some assumptions. All with physics, you make some assumptions, and these are crucial. And then you make computation. And unfortunately, for the readers who are not physicists, we don't know this assumption. They're obvious for physicists. So all I said, physicists, I mean real physicists, not this string theorists, immediately understand what I'm saying. Yeah. No, I'm not joking. Yeah, this it's really. Simple physics, very hard to learn it. I remember as a boy, in my library was this oldish book about this kind of experimental physics. Lots and lots of little phenomena described and explained. And I couldn't find it on the internet. I've forgotten the name of the author on the internet. And this is really fun to learn. It's like biology, many things, but each of them fit into the physical laws, which you can make computation and see what happens. And this incredible kind of knowledge. Now let's return where I begin. So I have to switch it again to. So. Now this about cells. So what else are there? Now, again, what are essential processes in the cells? And again, this terminology is metabolic chemistry is metabolism, chemical transformation there, and then reproduction of cells. And reproduction, of course, purpose of reproduction is generation, preservation of information. And this is the essence, of course, of life. There is information being preserved by replication. There are other mechanisms, by the way, which create identical copies, like protein in the cell. It's for different reason. But the major thing is that, and all metabolism on the cells essentially serve this purpose. And this chemical processes themselves, this metabolism, its informational component, that definitely there, which appears on two levels. But for all I understand, but it's certainly. But again, I don't know how they are related. So I don't know, and sometimes I manage to find something in the literature which is sometimes difficult. Namely, if you forget about kind of complicated things when there are not kind of pure chemistry, but synthesis of proteins, which is more complicated, but very simple chemical process, some components coming together or coming apart, and they are, as we know, they are controlled by enzymes. So what enzymes do? And again, what you find in textbooks and in most places, you see kind of repeating the same and the same words. And say, enzyme don't change, essentially, the type of reaction, we make them faster, and then the explanation that this enzyme, they kind of bring things together, and then blah, 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 and then complete absurd, and good indication of something being absurd are the same thing repeated everywhere. So you read there and there and there and there, you see the same, right? And it was said, sometimes you can go to the source, it was said something 100 years ago, to say something about enzymes, and then being repeated. And then the questions which, of course, appear, two questions appear. First, how enzymes work? Because if you look at a very simple chemical process, for example, the kind of common example everybody can observe, you have this, I forgot how called in English, H2O2. It's double bioxide of hydrogen. And it's present in our cells for some reason. And if you have this spit there, yes, oxygen goes out. It's used to sterilize because it produces molecular oxygen. And it's fairly stable. It have it's kind of a barrier. People systematically, you can see this picture. Just to, so I repeat this kind of words people say, which is completely absurd. So you have this landscape, yeah? And so you're sitting somewhere here. And you have to go from here to here. And certainly you gain energy when you go there, and potentially you have to go, but you have to go to the potential barrier and say, aha, with enzyme catalyze, they lower this barrier. How they do that? And then there are some kind of words which are not completely meaningless, but mostly if you start thinking about them, you just see that if you have proteins, and proteins are very kind of soft thing, which has very little energy inside, and this cannot work, because how this works anyway, how it works without any catalyzer, right? So what happens? So there is this energy, and in order to have this energy, and this goes kind of in quanta, it's everything on this level already quantized, and so you here have some water molecule which move fast enough, or several molecules which carry enough energy to make this jump, and you have to wait for that. And you can wait for a very long time, yeah, because time goes exponentially with the size of this barrier. It is a kind of. Actually, I couldn't find. I remember I read these mathematical papers. It's purely mathematics. You have a differential equation, and there is a potential. In what probability of time you need to press it, yeah, to go through that. This was very much advertised in recent time by Witten, kind of Morse inequalities. He does it for Morse theory. But there is very old papers. I remember I saw them and spoke to people about them, but couldn't find them. But it's this pure mathematics. However, so what protein can do? So if protein comes there, you have to break. If you have synthesized two things, then you can understand protein attract these two different molecules. They come closer, and probability of the hit, on one hitting another, they said, so somebody hits one of them, they stuck together, and then reaction takes place. Okay, you can believe it. You know, it's still, you cannot make it numerically satisfactory, but you can believe it. But what about breaking a molecule? So you have this H2A2, you have this 2 oxygen and 2 hydrogen, and they somehow brought this way, and this kind of... First, I must say, I don't quite understand quantum mechanically what it is. Forget about anything. So what, how this stationary equation comes, and how you know this, that. It's certainly elementary quantum mechanics, but I don't, at the beginning, know how to interpret it. I know what is Schrödinger equation, but I don't know how to measure this probability. Can one actually compute the spectrum of that and to say that there are 2 eigenvalues within certain size or what? This is probably what you have to do. The issue which arises here to understanding distribution of spectra of the Schrödinger operator. Probably. Again, I haven't studied this enough. But still, when this protein doesn't help you. So you add this protein, so it's stuck to a protein, something happening hefty. Still, if you make any mechanical, I thought about that. Easy to imagine because protein is big, something hits it, and then by one part, it hit the part. And I made this kind of heuristic computation, doesn't change anything, just 0. Just otherwise you would produce the Maxwell demon. In fact, enzyme works a little bit like Maxwell demons. They really wait for fast molecule. They take this molecule and do something. So, but because then energy is released, it's okay. So there is still no violation of the second law. Though for me, again, for physics it's something sacred. I mean, who cares for this law, right? If maybe not on this scale, but it's microscopically at some moment it violates. However, my understanding, what I found eventually in the literature, actually yesterday, after kind of browsing through lots of nonsensical papers, that what apparently happens mathematically in first approximation, that when you have a protein or any molecule, forget anything else. And this is some fact of quantum mechanics, which again, which I don't understand, that it undergoes, regardless, even if there is no environment, but you already have molecule which spend some time in some environment, so I have some residual temperature, which means that average energy of the molecule is given to you, but it moves. But now this motion of different nature, because covalent bonds, not the one which keep protein together, they're weak bonds. So there are 2 types of bonds, and that's essential, of course. One of the crucial things in life is there are strong covalent bonds in molecules, and there are weak bonds, how they stick together already. And this is by order magnitude are different. And this really is essential. But the covalent bond, they're much shorter. They're scale of fraction of angstrom, maybe 1/3 of angstrom, unlike it's not on the meter side. And therefore, they oscillate much faster. They're much stronger. And so I can imagine this is a bunch of atoms joined with strings. And they're very short string and a very rigid one. And so they oscillate faster. Not that they move faster, because energy must be the same, right? Energy per degree of freedom more or less the same, yeah, in Boltzmann distribution. But they oscillate much faster. And because they oscillate much faster, probability that some of them really accumulate energy of all of them, which happens kind of in Brownian kind of phenomenon, is by order of magnitude happens more often, and therefore the probability of hitting in the right places become higher, and therefore speed of reaction goes up. So the time scale changes. So what enzymes do, they change the time scale, the distance scale of oscillation of molecule and time scale. But again, I look at some articles not very carefully, but I don't think they even claim they can understand the orders of magnitude. So when you spit on this, how do you call H2O2 in English? Hydroxyl of hydrogen, whatever. Перекись водорода, как будет по-английски? А?
Нет, подождите, нет.
H2O2. Okay. Peroxide, yeah, peroxide. If you spit there instantaneously, it goes, so I think it's fast in reaction by order of 10 to the 6. And this 10 to the 6 a little bit more, because you see the scale you change here from weak to strong interaction, it seems to be only of order maybe of 100, but not of order of million. And so I'm not happy with that. Again, unfortunately, people won't say that they don't say openly, we don't know. Some I found papers which say, we don't know, and then you can trust what people say. When they start explaining something they don't know, it's rather annoying. about enzymes. So most of them, people, when you look at in most texts you find in the literature, sometimes they make some computation, which absolutely get it well. Presuming that you already from using something from experiments. Yeah? If you know how much you change it, how the rate reaction goes, this computation, you know, kindergarten computation. But what actually happened there, I don't think that it's known because I think it's very complicated mathematically. First, right, to understand how spectrum may be localized in big molecules. So it's a very interesting thing. So mathematically imagine the following picture. You have a graph, a relatively big graph, and kind of made, and their edges are strings. So you make it oscillate, and they have some kind of rigidity. And then it's oscillating, but then you look at kind of randomly how it behaves. So the measure will be distributed uniformly on the, usually on the energy surfaces, kind of Boltzmann distribution. But you want to know kinetic of that. How often some molecule will be, its energy will be of certain level. And then indeed you need a big protein, so the total energy will be rather big. And therefore it will be, when it localizes, it still will be big enough and the protein position in such a way to influence what happened there. So, of course, no chance to solve this equation, no chance to prove such a theorem, but at least to formulate it and to know what happens, right? So, if you don't take this into account, so I think you can prove it's impossible, right? So, there must be some phenomena on that, crucially depending on quantum mechanical phenomena. And they sometimes say, oh, well, there is this quantum phenomena of how we can go through the barrier of small energy, but again, without any computation, serious computation, even heuristic computation justifying that. Of course, you cannot do it rigorously mathematically, but you can formulate it precisely mathematically. No, there is quantum tunneling, and with quantum tunneling involved, but it doesn't seem to be quantum tunneling is a priori relevant there. Again, I don't judge by understanding mathematics, but by how I read this article, what people say, how serious in what they're saying. But at least I found some article where people start from, we don't know how the hell this works, but, and from that moment on you can trust them. Yeah? Like doctor, if a doctor comes immediately explain your problem, it's suspicious. Yeah? You must start saying, I don't know, if you mildly non-trivial problem. The same with these articles. Yeah? But so this mathematically, I think, absolutely interesting, fascinating problem. You have a bus of molecule moving by Brownian motion, and inside there is a graph, which have some rigidity, and you can describe it honestly in studying the equation, take into account spin to make it more fun, because when there are spin, of course, you completely have different spectrum. It very strongly changes the shape of the spectrum, which may be relevant here, maybe not, right? I guess I wish to know. And this may change indeed significantly the effect of spectrum. But and this is, of course, everything is known and understood for people who know physics, but I found I don't, unfortunately, had no chance to talk to anybody of them. But even forgetting that, is taking the isolation mathematical problem, I think it's not known. So what happens when you have this oscillation of many scales? Here is two scales of energy. As a mathematician, you say, what about more scales? You have this kind of highly heterogeneous situation and many scales of energy, and how it oscillates. I will look more and maybe on following lectures. It took me several weeks to find this already, what I found in the literature about enzymes. Yeah. But now, so where information comes in? So what the role of information in that? Even granted all this knowledge, which I said mathematically is still very far from going to the core of the problem, because so these enzymes are very specific for particular molecules. So they know something, so they carry some knowledge. It's like the key from the lock. You know, when you go to open the door, you run into the door, hit it, it's physics. But when you have the key, it's information, it is biology. It's a very different kind of logic, yeah? So somehow there is informational content. And this content of certain kind, and they kind of, it evolves by selection, and how fast it evolves, it's a very interesting issue which experimentally verified. It doesn't fit usual kind of naive ideas of probability. And this is one of the mistakes made apparently by Fred Hoare. I think so. I would be very careful criticizing a great man who knew physics definitely, unlike myself. And so it's one thing. So, and you know this key, lock and key picture of of enzyme you find in textbooks. It's certainly true in principle, but not in detail, right? So how much information you have to put into this to create enzyme? Number one, and how specific it is. And number two, so the role of enzyme is not just make reaction faster. So if you would just make all reaction faster, I guess you take bacterium and just make them universal. Enzyme make everybody faster, it will die instantaneously, it will be a tremendous mess. Somehow they balance the speed of the reaction is imbalanced in a particular way. And this is lots of information. So you have, say, 100 different enzymes, and what is the order in which you put the speed of this reaction. And so it's about 100 factorial, right, how you permute them. So there's huge information inside when being realized. Of course, in the DNA of bacteria, there is not so much information, right? 10 factorial is certainly a very big number. No, it's comparable maybe to, maybe not so big actually. It's 100 and there is something 2 to the 1,000 to 10,000. Yeah. So, I'm sorry. It's comparable. Yeah, it's comparable to the information in DNA. So again, I haven't made all this kind of computation, but of course they have to be done to see what we talk about. But the question still is how much the ordering of this enzyme is essential and how much it's encoded in form it's encoded in DNA, or just the speed themselves, or the speed simultaneously with when they're being used, and how much it involves in gene regulation. Of course, in bacteria, gene regulation is relatively simple, as we believe, yeah, right? But it may be. Okay, so I have another 2 words to say, and maybe I say the last sentence concerning information. So, how information goes in the cell. This is a kind of what is called Crick dogma, is it now understood. So we have DNA, so it's a chain of molecules. Let me show you the pictures now. See, I put them separately because when mixed with the text, they go into the random places and you don't know. So we speak in DNA, there are kind of 3 pictures reflecting 3 different things. This is the chemistry. They give you an idea of the molecules, how they made and how they fit. This is the geometry. It is a helical thing, and what is the size of that. And this is all kind of, you have to know that this is an essential ingredient. And this is a kind of, it's just the logic of that. So you have this background, it's just sugar, kind of one attached to another when there is no basis. It's really absolutely nice and periodic. And then you attach the basis to the background. There are 4 different letters, but they go in pairs anyway. So it's a binary, essentially binary information, right? This is DNA. And then this DNA being read, and you create RNA, which is a, no, where is RNA? No, in my picture. So it's segmented, so you segment. Here it is. So you segment into pieces. So you also add some little bit of information the way you segment it. So it's an extra way. However, it's already written how it's segmented, everything written on DNA. And you have similar sequence. That's again kind of simple, logically. Still it's a complicated mechanism, and here is an RNA polymerase machine which does it. This is a complicated, rather complicated machine. And then the next stage, again, logically simple, but much more complicated, probably the most complicated process which happens in cells and maybe in the whole universe, when you go from sequence in 2 or 4 letters to sequence in 20 letters, you go to amino acids, gluing them together into proteins. And there are some auxiliary processes here, but anyway, you have the sequence of, from RNA to proteins. Okay, still have another sequence. I mean, the process is complicated, but logically simple, right? You just, for each triple of letters, you create 1 letter. In 4 letters, you create 1 in in 20 days. And actually, this amazing kind of question here, how this was done. So it was known there are 20 amino acids, and there are 4 bases, and how the number 20 came from. And there was a fantastic paper written by Crick, by somebody, and they found mathematical explanation for that. That if you want to read something and just not to confuse without commas, you write something without commas and still separate words, you have to choose only particular triples, and there are exactly 20 you can make. This was a fantastic kind of observation, and happened to be completely wrong. One of the most beautiful kind of logical discoveries in biology, but happened to be wrong. In the nature, there's a very stupid way. You just put one after another. You know, there you go ta 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 ta, and it's very prone to mistakes, because the scheme which was suggested by Crick, I think with whom he wrote this paper, would be very stable, much less mistakes. But it's just nature didn't. Mathematically, it was too difficult for nature to come to that. You see, nature, when it finds algorithms, you see, it may have these programs, and you have to find this program, you have to search for this program by just brutal force, searching. Therefore, program must be easy to find. Therefore, programs which we have in biology, algorithms which are there, are very special nature. They have kind of this high level of complexity low. Not only the program is short, but it's easy to find, right? In order the program doesn't long, so it is short. It doesn't long for a very long time, and its finding is easy. So this gives you very much limit kind of program algorithm you can find in biology, and this is kind of fundamental feature in this information distribution. And I don't think it was seriously analyzed, because there is a paper of some computer scientist by what's his name? I forgot his name. About this probably approximately correct. He suggests kind of computer science approach to evolution, which I think completely besides the point. He developed some kind of formalism, but I don't think it ever applies to biology, because there's still very general algorithm. And here we have very, very limited class of algorithm. And I believe there's some reason to believe our brain works in the same way. We use certain program, but a very, very simple and very special one. And at some moment, in some next lecture, I give examples of such algorithm. So, and this is very ingenious suggestion by Crick with somebody, I forgot with whom it was. It was not correct. But still it's a very primitive thing. You take one sequence and just locally transform it to something else, very primitive algorithm, but now how you create structure. This is just sequences. They're just pure information. There is no substance to the sequences. And the moment is when they create proteins. And proteins, when they fold, and then they fold, their program works. What is the role of the Kolmogorov program? It's just following gradient of weak interaction of free energy for molecular chains, approximately, because there are some boundary condition of this or that nature. Well, what is called post-translation folding, but this is essentially that. So you know the program, the one which realizes everything there is that. It's just you follow gradient of the weak interaction in the molecules. And this moment, information becomes matter, and this is done by physics, so to speak. Biology, information not involved. And this is the interesting phenomenon. And it's everywhere, of course, in life. There is self-assembly. Things, once you give the right energy, but you prepare this, it's stuck in more or less by itself, being created like a very complicated structure as well, like ribosome and whatever. And of course, mathematics of this is certainly missing. Again, this is a process how it's stuck together. This is a kind of physics, but again, the difficulty for this kind of physics, it's not true in general. It's a very special situation when this happens. For generic systems, nothing like that happen. It will kind of, something will happen, but nothing of the kind, apparently, right? And this is an issue where you need kind of mathematical formulation of this speciality. And this speciality is describing it, again, a complicated issue. So life is very special. It's very far from generic. And again, saying it precisely, mathematically, is an issue. So everything I will be saying, I will trying to describe this simple biology in these terms. Hopefully, eventually, I can do it more more productively. Okay, so for today we finished. And if you have questions, if I can, most of course I can, hardly will be able to answer, but if you try, because my knowledge is on the verge of what I say, you know. Usually when you speak, they give a lecture, you give 10% of what you know. And here I give maybe 110, it's slightly more than I do. Yeah, so. But still it's kind of a mathematician fun to see there's so many things which you cannot explain and even cannot formulate, but you see the structure there. Because by your guts you feel there is a structure, and this mathematical structure, but it's very, very different from what you do in physics. And again, there are good reasons for that. And all the time I can make negative remarks about physics, not because I am negative, but the only reference points we have, right? From where we start arguing. And beside there is certainly this beautiful book by Schrödinger, which gives his physical perception of life, which I put, maybe a couple of days, I put on the internet most of what I said. I just organized in a slightly more systematic way. I don't know how to make pictures better incorporate into the text, because I haven't learned with latex how to put them exactly where I want them to be, because they choose their place by their own will and then become very inconvenient. Again, I couldn't find this way to do it better. But maybe I want to make the whole directory. I try to put on the internet if it works. If not here, do it in my current. Actually, this subject, if you look at my current lectures I had this year, and part of what I'm saying already there. So there it's somewhat easier to put it on the net there. Okay, so for today. So yes.